So today I'm going to tell you about sort of two problems. So one is about estimation in what's called the Z2 synchronization model, and then the second one involves sampling from the Sherrington-Kirkpatrick-Gibbs measure. But really what I'm going to tell you about is sort of a particular aspect of these problems, which is why I'm sort of presenting them together, which is proving the sort of local convexity of a certain free energy that is useful in studying these problems around stationary points of this free energy. Okay, and so I'm going to start by telling you about the first problem, and then I'm going to, try to give you some of the highlights of the proof technique and make that sort of the emphasis of what I'm trying to convey to you. So this tool that I'm going to talk about I call Sudakov-Fernique post-AMP. It sort of combines this Gaussian comparison inequality with the analysis of AMP algorithms. And the sort of takeaway message is that these two tools play very nicely together. Okay, so let's start with the Z2 synchronization model. So here the signal is n IID random signs, plus or minus 1. And what we observe are some noisy pairwise observations of the pairwise alignment of these random signs. So if xi equals xj, this product xi xj is 1, and we get a Gaussian observation of that. And if they have opposite signs, it's -1, and we get a noisy observation of that with a signal size that is described by this parameter lambda. Okay, so this is, you can think of this as sort of like a Gaussian version of a stochastic block model. So we have all the n vertices that have label 1, all the n vertices that have label -1, and for pairs of vertices that are in the same group, we observe a Gaussian with an elevated mean. For pairs of vertices which are in opposite groups, we observe a Gaussian with a depressed mean, and our goal is to estimate group membership up to sign, because there's no information in our observations about the global sign shift. Okay, so I can write this in matrix form. This is also just sort of a spiked GOE model with a certain structure on the spike X. Okay, so a lot is known about this problem. So for lambda smaller than 1, it's information theoretically impossible to achieve anything better than vanishing correlation with the true signal as n goes to infinity. And there's actually no sort of computation statistical gap in this problem. So for lambda bigger than 1, it's possible to achieve a non-negligible correlation with the true signal. And there's also practical algorithms which do so, and in fact, which achieve the sort of optimal information theoretic correlation with the true signal. Okay? So I'm going to talk about two approaches for performing estimation in this problem. So the first approach is an iterative approach. So we have, it's called an AMP algorithm. And many of you have seen AMP algorithms. If you've not, it's just an iteration which involves, does the cursor show up? Yes, it does. Which involves multiplication by our matrix, and then the subtraction of some term, and then we apply a certain nonlinearity to the result of that matrix multiplication. So it's the interlacing of a matrix multiplication with a correction and a nonlinearity. Okay, and so we're going to run this for a long period of time, and then for some large k, mk should hopefully be a good estimate of the underlying signal up to this possible sign ambiguity. Okay, there's another approach, which is to define what's called the tap free energy. This is a sort of data-based optimization problem, which we may attempt to optimize, and it's designed in a way so that the optimal value will hopefully be a good estimate of the true signal. Okay, so for the optimization-based approach, the problem is that this tap free energy is non-convex. It will in general have exponentially many stationary points, and so it's not immediate that optimization is a viable approach computationally. This is the exact form of this free energy in this problem. So it involves this this product with the matrix. These are sort of coordinate-wise entropy terms, and then we have this correction term. So you don't need to understand exactly where this comes from for the purposes of this talk, but it's a non-convex objective which has stationary points which are you can show that it has a stationary point which is a good estimate for the true signal. Okay, so this iterative approach and this free energy-based approach are related. So the fixed points of the AMP algorithm are exactly in one-to-one correspondence with the stationary, well, not just one-to-one correspondence, they are the same thing, the stationary points of the tap free energy. So actually, though these are two approaches, the problem of finding a fixed point of AMP is the same as the problem of finding stationary points of the tap free energy. Okay, so this is what's known about AMP. So this is sort of a Bayes optimal algorithm asymptotically. And so for any epsilon bigger than 0, I can, within finitely a finite number of iterations of this AMP algorithm, achieve an estimate which is sort of within a factor epsilon of the true Bayes risk asymptotically up to this sign ambiguity. But so what I should say is that this is for finite k. Some recent work has extended the analysis of AMP algorithms beyond finite k, but you still can't sort of take k arbitrarily large with n. So if I have n fixed and I just run AMP forever, we don't know whether that algorithm even converges. Okay. And so what we did with Zhou Fan and Song Mei in 2021 was we showed that the AMP algorithm in this Z2 synchronization model does in fact converge to a tap fixed point at fixed n, provided lambda is large enough. But of course, what we're interested in is not just lambda large enough. What we'd like to understand is any lambda bigger than 1, because this is the regime in which some partial recovery is possible and in which AMP sort of achieves that partial recovery. And so if we have trouble analyzing AMP, we might be interested in another question, which is, can we design any iteration, AMP or otherwise, which converges to one of these fixed points, either the fixed points of AMP or the stationary points of the tap free energy, which are the same thing?
Sorry, Mike, I just want to understand the distinction. So the results you're talking about at the top, they tell you that AMP gives you up to this epsilon Bayes optimal predictor,
yeah.
But it doesn't tell you that AMP actually landed at its own fixed point.
Well, so yeah, so after k iterations, it won't be at the fixed point. It'll be close to the, well, actually, yeah, it'll be close.
Do you know that it's close to the fixed point?
Well, no, now we do. Yeah, now we know it's close to a fixed point. But yeah, it's actually, you sort of, it's not even clear that there's, you sort of believe, you find a point that sort of is approximately a fixed point, but that doesn't tell you that there's actually a fixed point nearby. What we will do actually is, because the tap free energy is related to, has this stationary points which agree with the AMP fixed points, once we show that the tap free energy has some region of local convexity, that actually allows us to locate in a close proximity an AMP fixed point.
Okay, so what you get from the top flavor result is that AMP, after k iterations, gets close to some notion of approximate fixed point. But
yes.
You don't know that that approximate fixed point has much to do with a real fixed point.
That's right, yeah.
Okay, thank you.
The top also is about something that's optimal, right? Because it's not special initialization.
Yes.
Right? So that's something that's already correlated.
Yes.
Right? And for your work with spectral initialization, or is it for every?
Oh, so this is for spectral initialization.
So yours are also with spectral initialization. So you show the level of complexity around that fixed point.
So it's not about around all fixed points or something. Yeah, yeah, okay.
Sorry, that fixed point means the one that.
So there's lots of fixed points of this free energy, some of which might not actually be very, close to the true signal. So what AMP does, though, is it does correlate, or in the spectral initialization, it does correlate with the signal, and then you run it, and it gets close to a fixed point. And that's sort of the fixed point we care about. Okay. Okay, so what we show in this paper is that for any lambda bigger than 0, then there's some sort of small ball around the Bayes estimate, okay, for the signal. And in this small ball, the capture energy is locally strongly convex and has a unique local minimizer. Okay? And so what this allows us to do is to design an algorithm. It's not an AMP algorithm entirely, which converges to this good fixed point. And it's a two-stage algorithm. The first stage is to run AMP, and the second stage is then once you arrive in this small ball of local convexity, you can just use a convex optimization algorithm, in this case natural gradient descent, which is basically mirror descent, which will converge to the fixed point, yes?
Wait, so if there's so many fixed points around the base of Sudakov, how do you actually like use
No. There's
I'm saying like outside the restaurant involved, there's still a lot of
right. Okay. So AMP is just the iteration I showed you. It's exactly what I showed you. And the way you analyze AMP is not by doing a landscape analysis. You just do some sort of statistical analysis where you understand the statistics of those iterates without reference to a landscape. And then once you get into this ball, you do a sort of landscape analysis. And what I'm actually, this is sort of, and maybe, I hope I'm answering your question. This is sort of, the message I'm trying to convey is, and what the Sudakov-Fernique post-AMP proof strategy does is it allows you to sort of handle these two types of analysis in one. Okay? So one is sort of a statistical analysis for the AMP stage, and then one is then more of this worst case analysis for an optimization stage.
You also have spectral visualization.
Yes. Yes. Mhm.
It's explicit,
Sure.
spectral density
So yeah.
not closed, the AMP is
Sure,
closed,
sure.
and then finally,
Yes. Yeah, so 3-stage. Okay. Okay, so 3-stage, I should say. Okay. But okay, so there's a, but okay, maybe if we want to combine the first two stages. The point is there's sort of a statistical stage, which is sort of spectralization in AMP, and then there's a sort of a worst case stage. Okay, and this is, a type of, this sort of two-stage analysis, occurs elsewhere for analyzing statistical problems. Okay, so what this proof technique is, and I'm not going to go through all the steps of the technique, I'm just going to sort of highlight this one part, which is this sort of comparison inequality, which is a tool for sort of probing a landscape property. Well, the way I think about it is that one of the things you can do with it is you can probe a landscape property locally around an AMP iterate. Okay? And it reduces sort of a question about the curvature of this objective, say, to the study of a certain deterministic low-dimensional saddle point. I'm not going to sort of describe how you analyze that deterministic low-dimensional saddle point problem, not because it's easy to analyze, but because there's maybe various ways to arrive at it, and I'm going to emphasize just one way to arrive at it that I think is, hopefully broadly useful. Okay, so the way I'm going to sort of describe to you what this Sudakov-Fernique post-AMP inequality is it's really sort of a combination of two techniques, which I'll describe first. So one is state evolution for AMP algorithms. The second is, the classical Sudakov-Fernique inequality, and then Sudakov-Fernique post-AMP sort of combines the two. And so what AMP and state evolution are, they give you a tool for analyzing, a certain class of iterative algorithms. What the Sudakov-Fernique inequality does is it allows you to study the maximum value of a certain Gaussian process. And then, Sudakov-Fernique post-AMP will sort of allow you to do both. Okay, so let me just tell you about approximate message passing, and this will be review for many of you. And the sort of main thing that the state evolution analysis of AMP algorithms allow you to do is they allow you to reduce an iteration that involves a GOE matrix. So this is, complicated to understand, to a much simpler iteration that just involves high-dimensional Gaussian vectors, which are, easier to understand. Okay, so let me just show you what that reduction is. So I showed you what the AMP algorithm was for Z2 synchronization. This is the AMP algorithm for, in a more general, this is a more general sort of way of writing a class of AMP algorithms, which will, hold for any choice of these functions fk. But it's basically what I've already shown you. You sort of, multiply an iterate by a random matrix, your random matrix W, add some correction term, and then you apply a nonlinearity to get to the next iterate. Okay, so it's an iteration involving a high-dimensional random matrix. And the state evolution is just a sequence of Gaussian vectors. Okay, so the Gaussian vectors indexed 1 through k, and then I index the coordinate of the Gaussian vector. So these Gaussian vectors, their coordinates are drawn IID, and they're jointly Gaussian with some covariance matrix k that I'll tell you about. And you just use these Gaussian vectors as the sort of sequence of vectors to which you are applying your nonlinearity. Okay, so this is somehow easier to understand because there's no random matrix. There's just this covariance matrix K, which describes the relationship between different iterates. Okay, now just to allow me to speak more clearly or easily, I'm going to refer to these G's as the sort of AMP noise. They're Gaussian vectors. And then once I apply my nonlinearity, which you should, in the context of a statistical problem, think of an estimator, I'll call it my AMP estimate. Okay, so in the interest of time, I'm going to maybe not spend that much time on this slide. So this is a formal statement of the state evolution, and without trying to unpack it entirely, it just says that in some sense the AMP iterates have a distribution which converges as n goes to infinity to the joint distribution of these Gaussian vectors. Okay. So this is what I really want to emphasize, which is what is this matrix K, which is the covariance between AMP iterates, and this is what's going to connect the three methods that I described. Okay. And so the way I think about it is that K is chosen so that the geometry of the AMP noise is the same as the geometry of the sort of AMP estimates. Okay? In particular, their sort of second moment structure agrees. Right? So if I look at the empirical sort of second moments and correlations between the AMP noise vectors, I'll get the same thing approximately or asymptotically as I would if I looked at the second moment structure of the AMP estimates. Okay? And there's only one matrix K for which this sort of sequence of Gaussian vectors with the AMP nonlinearities will have this property, and that's the K that you want to choose. Provided you choose that K, you'll get that this state evolution describes the AMP algorithm. Okay? So here again is the AMP for Z2 synchronization. I have my sort of AMP estimates, and then I have these H's, which, okay, this is writing things in a slightly different way, so these are sort of non-centered Gaussians, but the state evolution of this will be such that the geometry of the M's is reflected in the sort of noise of these H's. Okay. So now I'm going to tell you about the Sudakov-Fernique inequality. I'm going to try to tell you about it in the same format so that you start to understand the connections I'm trying to make between these approaches. But what Sudakov-Fernique does is you start with a high-dimensional optimization problem involving a GOE matrix. So actually, the Sudakov-Fernique inequality is like a general Gaussian comparison inequality. I'm talking about it in the context of problems involving a GOE matrix. But okay, so you start with a high-dimensional optimization problem involving a GOE matrix, and I'm going to reduce it to an optimization problem that just involves a single Gaussian vector. So it's a similar sort of simplification as occurs in state evolution for AMP. Okay? So in particular, I get to look at optimization problems that take this form. Okay? So there's this matrix term, and then there's this deterministic part of the objective, F. And what Sudakov-Fernique will do is it'll allow you to reduce your analysis to the study of this arguably much simpler problem, in which the matrix term is replaced by some term that involves the argument, and then this quantity xi, which is a Gaussian vector. Okay? So the precise statement here is that the sort of minimum value of this objective involving a Gaussian matrix is stochastically larger than the minimum value of this analogous objective involving a Gaussian random vector. And the way I'm going to write it is the following. I'm just going to define this vector gm, which is this Gaussian vector xi times the norm of the argument m appropriately renormalized, and look at this first term as the inner product between this g of m and m. Okay? And this is what stochastically larger than means. Okay, and the reason I'm going to write it in this way is because I'm trying to sort of evoke similarities to this AMP state evolution. You see, this GM, one way to think about it is it's like a Gaussian vector whose geometry, in a certain sense, is the same as the geometry of M, where now by geometry I just mean norm. Okay, so the norm of this Gaussian vector is sort of determined implicitly by the argument, and you choose them so that they agree at least in the sort of, at least in one second moment statistic of their geometry. Okay. Now, let me try to draw, connect this to the problem I'm interested in, which is the curvature of the tap free energy around an AMP iterate. So the way you can sort of study the curvature of the tap free energy around an AMP iterate is you write the minimal singular value of your Hessian in a form that is handled by the Sudakov-Fernique inequalities. So in particular, the sort of minimum value in some ball, there should be some square root of n here that's missing, of this singular value can be written in this way. So it's the joint minimization over points in this ball, and then this sort of direction that probes the direction of minimal curvature of your tap free energy of some term involving your GOE matrix, and then some f, which comes from the complicated expression I wrote on the previous slide, but it's not really important exactly what it looks like. Now, the question is, can I just make this replacement that's made by the Sudakov-Fernique inequality and say that the minimal value of this singular value in the ball is lower bounded by sort of the analogous minimal value with this replaced Gaussian process? And the answer is no, because now I've sort of, this MK, which shows up in my constraint set, is itself a function of the random matrix W. Okay, so there's some, the optimization problem itself is a function of W, which is not something that is directly handled by the Sudakov-Fernique inequality. And so what the Sudakov-Fernique post-AMP inequality is it's not really a new inequality. It's just the Sudakov-Fernique inequality conditional on the AMP iterates. And so you might say, okay, why is that a big deal? And I think the main thing I want to convey is that if you make some approximations once you do this replacement, you can sort of see that this inequality takes a certain form that respects sort of the geometric intuition that I've been trying to build so far in this talk. In particular, this sort of is a lower bound, provided you just redefine what I mean by G of U. Okay. So now finally we've arrived. So we start now with an optimization problem involving a GOE matrix where now the constraint set is allowed to depend upon some iterates that were generated by an AMP algorithm using the same matrix. And we get to lower bound it by what looks like the objective that shows up in the unconditional Sudakov-Fernique inequality, except that we're going to redefine this G of M. And we're going to redefine it in a way that is sort of reminiscent of the intuition I've been building so far. In particular, we're going to define this G of M so that its sort of geometry relative to the AMP iterates agrees with the geometry of the optimization argument relative to the AMP estimates. Okay, so in particular, remember the AMP iterates are such that the geometry of the estimates is sort of in correspondence with the geometry of the AMP noise. And so there's sort of an approximate isometry that rotates estimate space to noise space. And what this G does is it takes the argument to my optimization objective, and it performs that rotation on it. So you should think of this as it projects the argument onto the space of the AMP estimates, and then rotates it into the space of the AMP noise. And then to the extent that the argument is orthogonal to the space of the AMP estimates, it just introduces a new Gaussian noise vector and rotates, or doesn't really rotate, but adds a component of this G in that direction to the extent that U is orthogonal to the span of the AMP estimates. Okay, so the way to think about this is that G of M, the second moment structure of G of M in G1 through GK is the same as the second moment structure of M and M0 through MK. Okay, And provided you sort of now define G in this way, which I think is natural, given the intuition we have for the AMP estimate, the AMP state evolution and Sudakov-Fernique, you do get not a sort of finite sample comparison inequality, which is what the Sudakov-Fernique inequality is, but sort of an asymptotic comparison inequality, because I've had to make some approximations and replacing things by this G. Okay? So in particular now, I get that in the limit as n goes to infinity, the minimal value of this optimization problem that involves the GOE matrix is lower bounded by the asymptotic minimal value of this Sudakov-Fernique lower bound. Okay. So, all right, so that's the part of the argument that I wanted to sort of show to you. So far, what I've shown you allows you to reduce the optimization problem into sort of the analysis of a k-dimensional optimization, which is still maybe not very satisfying because k could be, even though it's finite, could be very large. It could be like 100 or 200 or something. But there's sort of a second step, which I'm not explaining to you, which is that some magic happens once you make this reduction, and you can actually ignore most of the directions except sort of the most recent AMP iterate. So you actually arrive at a low-dimensional problem, which is sort of equivalent to the original low-dimensional problem that we analyzed in our first paper, where we didn't use this Sudakov-Fernique post-AMP technique. Okay, so this is the statement of the theorem again. A late-stage AMP iterate is in a region of local strong convexity of the tap free energy. That region contains an AMP fixed point. Okay. Now, there's a second, application of this technique to a problem that I'm just going to go through very briefly because I don't have really much time left. But this involves trying to draw a sample from the Sherrington-Kirkpatrick Hamiltonian, which I've written here, and recently Alawi, Selke, and Montanari used this stochastic localization technique introduced by Eldon, in which you essentially define some stochastic differential equation whose deterministic part involves the mean of some tilted version of the Sherrington-Kirkpatrick Gibbs measure. And the idea is to compute this mean approximately using an AMP algorithm. And so this is, and so what they in fact propose is that you compute this mean by doing this sort of two-stage thing, where you first run AMP and then you use local natural gradient descent on a sort of version of the tap free energy that's tailored to their problem. And they show that if you do this, then you sort of sample from the Gibbs measure in the sense of getting a drawing from a measure that's close in Wasserstein 2 distance to the Gibbs measure. And they're able to show this for beta less than 1/2. And the reason they don't do it for beta between 1/2 and 1, which is the sort of regime in which they believe that it's possible to do this sampling is beta less than 1. There's sort of just a small technical barrier in the region 1/2 to 1, and that's because internal to their proof, they need to show some Lipschitz property of this posterior mean in Y, and they use some local convexity of the tap free energy, which they're not able to show using beta for beta between 1/2 and 1 because they're just using some sort of eigenvalue type of argument. And so this type of analysis with Sudakov-Fernique post-AMP very readily allows you to establish this local convexity using the same argument I've described, and you can conclude from that this algorithm succeeds in this Wasserstein 2 sense for the entire sort of easy regime, which is beta less than 1. Okay, that last part was very brief, so I apologize for that. So the summary is that there's this asymptotic comparison inequality for probing landscapes around the AMP iterates. I've only really applied it successfully to these two problems so far, but I do believe it's sort of potentially useful much more broadly. My intuition is that potentially a lot of simplification will occur when you arrive to these low-dimensional problems in a broad set of statistical problems. And in fact, there's sort of a large class of algorithms, including gradient descent and other first-order methods, which can be reduced to AMP algorithms. And so I think, the use of this sort of technique for probing a landscape around the iterates of a general first-order method could be, possible and is worth investigating. And there's also a theory for sort of regression type problems that involve a different type of Gaussian matrix, which I think maybe are also amenable to this type of technique. And I'm currently working on that, but I think hopefully this is a fruitful direction. So that's all I have to say.